Today's video, we will introduce you to logarithms. This may be a video you're going to have to pause and rewind and look at, maybe in more detail than any you've had to at this point. It's a very new concept for most students. This is really the first time they're really introduced to logarithms. So please use the video as you need. And as I said, it may take time to get your brain wrapped around these. And that's just normal because it's something that's very, very new to you. Don't be discouraged. Just kind of keep working away at it, and at the very least, give yourself some sense of what logarithms are and how they work, and get the basics of this down. Just a bit of the history behind logarithms over here. John Napier is credited with developing them. And the odd thing about it is you're going to find out the logarithms really are exponents. But in the history of mathematics, if you look at a timeline, logarithms were actually being worked on before anyone ever worked on exponents. So it's kind of one of those oddities of mathematics where one would probably, just because of the way we learn things, we learn exponents first and then logarithms. We kind of just in our heads think that that's the way that naturally they progressed and were uncovered. But it's actually the opposite. Logarithms were uncovered before exponents. And it's funny how they talk about this part here is a close-up of a pine cone. And over here you have the horns on this ram. And mathematically speaking, these and the pattern you see here follow very, very closely to logarithmic functions, which is kind of odd how some of the things that happen in biology will kind of translate into mathematical functions. Okay, so let's get going here and have a look at what are logarithms. Well, we're going to first just refresh your memory on inverses. So recall from inverses. Inverses, essentially, if you have a set of x values and a set of y values, if you recall here, when you go to the inverse, that's the notation for inverse, basically what happens is your x and your y's switch. So these would now be your y values. I just have them color coded here, I guess. And here, so these would now be what used to be the y's. This would now be 12, 13, 14, 15, and 16. And this would switch and become 2, 3, 4, 5, and 6. That's by definition inverses. They switch x and y. Inverses can be demonstrated visually. If you had these ordered pairs on a graph, their inverses would be these ordered pairs. That we say that the inverses are always reflections across the line y equals x. This is the line that goes up through your origin with a slope of 1. So this one, let's just pick one of these, for example. This is the ordered pair 1, 1, 2, 3, 4, 5, 1, 6. So its inverse would be 6, 1. There it is right there. Those two reflect across that line. And you can do that for each of these points. Okay, so that's, again, I'm just trying to get your brain thinking of inverses. Here's a little word association game that I usually would play with students. I'd say, okay, if in your head, if I said, I'll give you a mathematical process, you tell me what you would perceive its inverse to be. Well, I think if I said addition, our natural reaction would be, the inverse process is subtraction. Subtraction will undo addition. Multiplication, if I said, what will undo multiplication? I think we would all say, well, that would be division. Squaring, if I wanted to undo squaring, I would take the square root. If I took the sine of a function, think trigonometry, the sine of an angle, well, then I would take what's called the inverse sine to undo the sine ratio. This one is where you might be at a bit of a crossroads right now. Say exponential. How do I undo something like y equals 3 to the x? That's not something we've run into. Well, you can probably guess where this is going. That is what, in fact, logarithms do. Logarithms are the inverse processes of exponential functions. So, for example, if we graphed y equals 2 to the x, this would be some points. So if x was 0, 1, 1, 2, 2, 4, these are these points over here. If you had -1, you'd get 2 to the negative 1, which is a half. 2 to the negative 3 is negative 1/8, or sorry, is 1/8. 2 to the negative 4 is a quarter, so 0.25. And you get these points. You'd have an asymptote. We talked about asymptotes. It'd be getting closer and closer to the x-axis. If you switched all those points and graphed them, okay, so if I switch those, basically do the inverse, so these are going to become the x's, and these are going to become the y's. Let's have a look at that. Oops, I went too fast. Let's look at that graph. So if I switch them, look at this graph. Well, if you recall what the other graph looked like, I'll just back up for a second. Look like this. Look at this new graph. Looks like this. Those two graphs are inverses of each other. They are the reflection of each other in the line y equals x. Okay, well, I want to show you. I just used 3 to the x as another example. And I went to Desmos, and I graphed y equals 3 to the x. It's in red. And then I graphed y equals the log of x. The way you say this is y equals the log of x to base 3. If you look at these graphs, hopefully you look and say, hey, those are the inverses of each other. They are the reflection of each other. Here's your y equals x line. This line is, or this graph is the reflection of this graph in the line y equals x. So I can see that the function, the logarithmic function, log of x to base 3, the base here is the same as this base, is the inverse of 3 to the x. So that's kind of where we're going to go with when someone says, well, what are logarithms? They're the inverses of exponential functions. Okay. All right. So let's look at the notation of logarithms. So basically, if you have this statement, we'd be okay with this. So this would be considered your base, and this would be considered your exponent. So what we want to be able to do is now realize that that statement can be changed to this statement. Y, the exponent, equals, now the way you say this is the log of x to base a. So you don't say log ax, you say log of x to base a. So to translate this, well, sorry, let's just go over here. And this should be a kind of a two-phase process. You should be able to start with an exponential statement and write it as a logarithmic statement. You should be able to start with a logarithm and write it as an exponential statement. So for example, if I had y equals 7 to the x, and I wanted to switch that and write it as a logarithm instead, well then it would be x equals the log of y to base 7. So one thing you'll notice is the base of the exponential statement coincides with, this is called the base of the logarithm. So it's like the opposite of an exponent. It's a subscript written down below here. And if someone says, well, what is a logarithm? Well, let's look at, here's a logarithm. This is what it equals. It's an exponent. You're trying to figure out what exponent you have to raise up a base to in order to get some value. So for example, if I wrote out the log of, what we could do in our head, 27 to base 3. So at this point, most you say, I don't even know what that means. This is what it means in words. A lot of times when you put it in words, students can say, okay, I see what you're saying now. This is saying 3 raised to what exponent will equal 27. That's what the log of 27 to base 3 would equal. Okay, so if I wrote out log, actually let's answer this. The answer to this, it would be equal to 3, because 3 raised to that exponent would give me 27. The log of 100 to base, let's say 5. means 5 raised to what exponent gives me 100? Well, the answer is somewhere between 2 and 3 because 5 squared is 25 and 5 cubed is 125. So I'll eventually show you how you can do these on a calculator. Depending on your calculator, some of you may have calculators that let you type this exact statement in. Most don't, so I'll have to show you how you can use, there are certain bases on calculators that you can do. I'll show you how you can use those to kind of manipulate your way through some of these other bases. We'll get to that later on. Okay, so let's just talk a little bit here more about this notation. So this is exponential. We have to be able to write it like this, and we have to be able to switch back and forth. So kind of pay attention to where the x is here and where it shows up here, where the y is here, where is it in this one, where's the base here, where does it show up here. A couple things about logarithms. The base, it's got to be positive. You cannot have negative bases when you're dealing with logarithms. And I want you to think about that, because if you have negative bases and you start raising them to exponents, well, all of a sudden, if you try to raise it to, let's say, a half, and you have a negative base, right? So if I had -3, and I wanted to raise it to the half, well, half means square root. That's not possible. So I want to avoid undefined situations. So we never make the base negative, and we never make the base 1. Because think about if the base is 1. Well, if this is a 1 raised to any exponent, there's nothing I could have here besides a 1, right? Because 1 to any power is always 1. So we don't use 1 as a base either. Okay, so make sure you understand the bases of logarithms will always be positive, and they will never be equal to 1. This part here, I'll notice up here, I just saw it in my, this is called the argument of the logarithm, and this is called the base of the logarithm. So for example, if I said log m to base x, m would be the argument, and x would be the base. All right, so let's look at a couple of examples just switching between the two notations. So if I have 3 to the exponent 3, and I wanted to change that to a logarithm, well, the base is 3. Remember, the logarithms are equal to exponents. So this one should be the log of 27 to base 3 should equal my exponent. The log of 27 to base 3 equals my exponent. Next one should be the log of 256 to base 4 should equal my exponent. The log of 256 to base 4 equals the exponent. The log of 128 to base 2 should equal 7. The log of 128 to base 2 equals 7. The log of 27 to base 1/3, again, that's okay, as long as it's positive and more than 0, and not equal to 1, that you can have fraction bases, it would equal our exponent. And all we're using here is this basic premise that the log of x to any base, if that equaled y, let's say, that means b to that exponent is equal to x. Remember, logarithms are exponents. So the y, which is the logarithm, is written as my exponent. And I put a double arrow on it because in that one we started here and we worked this way. The next slide we're going to start here and we're going to work this way. All right. So here, it's always going to be the base to this exponent will equal the argument. So on this one, it would be 2 to the 6th equals 64. This one I kind of like the pattern. It's kind of like circling around. So 2 to the 6th equals that. That to that exponent equals that. That to that equals that. You kind of get a pattern following out of this one. Let's have a look. So 2 to the 6th equals 64 is right. So this one should be 25 to the exponent 1/2 should give me 5. 25 to the 1/2 gives me 5, which it does, because 1/2 means square root. Square root of 25 is 5. 8 to the exponent 0 should equal 1. 8 to the exponent 0 equals 1. 1/3 to the exponent 2 is not going to equal, that should be 1 over 9. This should have been, there's a typo on here. I forgot to fix. This should be 1/9. So 1/3 squared would give us 1/9, and it would. Here it is. 1/3 squared is 1 over 9. All right, so that's switching from a logarithm to an exponential. Prior slide was exponential to a logarithm. All right, let's have a look at some examples. I'm trying to figure out what x is in each of one of these. What I'll often do with logarithms is just switch them to exponentials. So 1/3 to the x, so 1/3 to the exponent x has to equal 27. Well, 1/3, I could write it as, so this goes back to now, this is why it falls under the unit of exponential functions and relations. 1/3 is 3 to the -1 to the x. 27 is 3 cubed. Well, if I multiply those, I get 3 to the -x equals 3 to the 3. So do you recall now doing exponential equations? If the base is the same, the exponents have to equal each other. So I can, from this, surmise that -x has got to be equal to 3, which means x must be -3. Okay, this time the x is the argument. Well, this one's going to be really easy. Same thing, switch notations. 5, base 5 to that exponent would have to equal your argument. 5 to the 3 is equal to x. That means that that would have to be 125. This one, x squared would have to equal the fraction 1 over 9. So if x squared is something and I'm trying to figure out what x is, well, I would just take the square root of it. So x would be 1/3. X can't be a negative, so we're just dealing with positive square root here only. And this one would be another easy one, much like the one above it. 3, the base here, raised to this exponent, would have to equal your argument. 3 to the 0 is 1, equals x. There's something called common logs. Common logs are base 10 logarithms. Our number system, metric system, is based primarily on number systems of 10. So it is a logarithm where if you just write out log 3 and you don't put any base here, it is understood that you mean 10. You do not have to write base of 10 in there. It is what is referred to as common log, and it is, because it's used so commonly, we do not have to write it in. It's understood. Therefore, if I go log of 3, I know that this means, even though it's not there, it means base 10. It means 10 raised to what power gives me 3. So if I say, okay, everyone, you get that? And you say, yep, I get it now. And if I said, okay, what's the log of 1,000? The log of 1,000 equals, you said, I'm not sure. Well, this is where you got to understand what logarithms are. There's no base there. It means it's 10. This is saying 10 raised to what power will give me 1,000? Well, 10 to the power 3. So the log of 1,000, is 3. Grab your calculator and look on it. You will find a common log button. Now, I don't have it here to demonstrate, but it will just say log. And usually right next to it, there'll be another one for ln. So this one is, as I just told you, it's called common log. So if you wanted the log of 1,000, you could just type log 1,000, hit enter. Some of you will have to do the opposite, put 1,000 first, then hit the log button, and it will tell you the answer is 3. It's telling you 10 to what power gives you that value. ln is called natural log. We use this more when we get to calculus. And it is a logarithm. It's another popular logarithm, but more so for advanced level maths. And it's a logarithm with base. So this is common log. We said it's base 10, this one. Natural log is what's called base 10 here, base 10. These are called base E. E is a mathematical constant called Euler's number, E-U-L-E-R. Euler's number is something like pi. It's a mathematical constant that has an application in calculus, which if you're continuing the pre-calc stream and end up in our calculus program, you'll learn much, much more about natural logarithms. I want you to at least know they exist and what that button is in your calculator. Euler's number is roughly 2.718, and it's like pi. It's irrational, non-terminating, non-repeating. You can find it on your calculator. It's always the inverse, or it's the second function of this one. You'll usually see above this button on a calculator, E. It'll be e to the x, maybe, something like that. That'll be your second function. So you want to know what is e and what more decimals than I've got here, just put in e to the 1. And that'll give you Euler's number raised to the first power. Again, don't worry too much about natural log yet, at least other than knowing that it does exist. But common log is something we are going to run into quite significantly. So just to recap, what are logarithms? Well, logarithms are inverses of exponentials. So they're a way to figure out exponents that you would raise a base to in order to get a certain value. We talked here about the base has to be positive, can't be 1. I said that a second ago. Logarithms are exponents. What is a common logarithm? It's a logarithm with base 10. What does a graph of a logarithm look like? Remember, they're inverses of exponentials. So I quickly showed you, I did 3 to the x, but let's use, there's 2 to the x. Here would be, I'll do it a different color. This would be the log of x to base 2, which is considered the inverse of 2 to the x. And notice their graphs are mirror images of each other. Oh, I didn't do that right, sorry. This should have crossed. Let me try this again. Because it should. The asymptote here was x equals 0, so the asymptote here should be y equals 0. And this one went through 0, 1. This one should pass through 1, 0. So my intercept backwards. This will go here. Your graph, your asymptote would be y equals 0, so your graph would come up. Oops. Sorry about that. Your graph would come up like so. Head out this way. And then you have your asymptote here. So this would be the graph of y equals log of x to base 2. We don't do a whole lot with graphs of logarithms, other than we'd like students to have a general idea of what shape they are. They are, as I said, the inverses of exponentials. Just keep that in your mind, because I think most of you have some idea of what an exponential looks like. So in your head, say, well, what would happen if I flip that graph across this line y equals x? What would it end up looking like? And that'll give you an idea of what a logarithmic function looks like. And as I mentioned, common logarithms are base 10. So I also always encourage students to understand, try to, in words, what a log is. So if I said, what's the log of 16 to base 2? The answer is 4. Sometimes in the beginning, students are slow because this is new. That's what I told you. It's new. You're not used to it. Oh, why is it? I don't get it. Why is it 4? This means this base, 2, I'm going to put it in words, 2 raised to what exponent will give 16? That's what the log of 16 to base 2 is equal to. Versus up here, if I just write log of 100 with no base, that implies I'm talking about base 10, common log. I'm saying 10 raised to what exponent gives me 100? Answer is 2. And again, there is a button on your calculator that will do base 10, guaranteed. Some of you will have buttons on your calculator that let you input any base, which is going to be a nice feature to have on a calculator. Okay, so that's just a recap of that. This is the same information. It's just from your textbook. It's the recap at the end of the introductory section in the logarithms unit. So what I'd like you to now do, this just covers everything I've already talked about, but you could certainly print it off and have it for reference. It's in your notes. So I put all these notes under your class notes in your class notebooks. And let's do a couple of these. So I'll do these first just to show you. So if I wanted to figure out the log of 8 root 32 to base 2. Well, what I might be able to do is say, I don't know what that, I can't tell but just by looking. Sometimes you can tell just by looking at it, but this one I can't. I'm going to say, well, I don't know, let's make it equal x. And now I'm going to switch it from a log to an exponential, just because we're much more confident and comfortable with exponential work. 2 to the x has to equal 8 radical 32. Well, this could have been a question in our exponential equation section. 2 to the x, these are powers of 2. Let's change them to powers of 2. 8 is 2 cubed. 32 is 2 to the 5th. Square root is a half. This is going to be 5 halves. This is going to be 3. I'm going to add those exponents. So 3 over 1 would be 6 over 2 plus 5 over 2. So it's 2 to the 11. Did I do that right? Let me see here. 3 over 1. And I'm going to add the exponents. I'm going to multiply those together. 3 over 1 plus 5 over 2. So this would be 6 over 2 plus 5 over 2. This would be 11 over 2. Now the exponent has to equal each other. Now another way to think of this is if I had just did the whole change everything to powers of 2 here and said the log of 2 to the 11 halves, because that's what this all right side ended up equaling. If you understand what a logarithm is, well, the answer here is obviously 11 halves, because this means 2 raised to what exponent gives me 2 to the 11 halves. Well, the answer's got to be 11 halves. That'll be a property we talk about in my next video. All right, so that one's 11 halves. This one would be x to the negative 2/3. X to the negative 2/3 has to equal 81. I want to know what x is. We did this earlier on as well. You raise it to the reciprocal. I think this is a pre-calc 11 trick. So the reciprocal of this, and I want to get 1, not negative, so it's going to be negative 3 halves. That means I have to put the other side also to the negative 3 halves. When you multiply these two together, you get x to the 1. Now, this means 81 to the negative 3 halves. So the bottom number means take the square root. So the square root of 81 is 9. And then I have to cube it. Grab my calculator for that one. Don't know that off the top of my head. So 9 cubed is 729. So this would be, just so I don't want to go jump right to the answer, but it means 1 over 81 to the 3 halves, because it's a negative exponent. You take the reciprocal and make it positive. 3 halves means, so bottom number, take the square root of 81, and then after you get your answer, cube it, and that's where I would arrive at 1 over 729. All right, let's look at this one. Same as the one up here. Right away, I notice this is a power of 5, so I'm going to just do this one, the other strategy. I'm going to switch it, because I can write it as the same power as my base. 125 is 5 to the 3. Well, let's switch that to 5 to the negative 3. So now, translate this into words. This is saying, this is your argument, this whole thing here. 5 raised to what exponent will give me 5 to the negative 3? That's what this means. The answer is obviously negative 3. Now you could do it like this one. Make it equal x. 5 to the x equals that. Solve it as an exponential equation. Same thing. This one, I think I'm going to go the strategy where I make it equal x. I'm going to go root 6 to that exponent. So radical 6 raised to what exponent will give me 36. I'm going to change this to 6 to the half. That's root 6 to the x. I'm going to change 36 to 6 squared. 6, multiply these together. 6 to the 1/2 x has to equal 6 squared. So that means that the exponent, because they're both base 6s on each side, the exponent here has got to equal the exponent here. So 1/2 x to equal 2. I'm going to double both sides. X would have to be 4. Okay, so in all of those examples, the key for me to be successful was understanding that logarithms are just exponentials. And I'm trying to unravel, what do they mean exponentially? What are they asking me to figure out? So I kind of, here I wrote it out. Here I just said I knew it was trying to get me to figure out 5, but what exponent would give me that? So I just changed that to a power of 5. So So I could clearly see then that 5 would have to be raised to the -3 to get that expression. Okay, so at this point, you should now take a look at just some of these properties. As I've stressed before, more so in this section than any, this is brand new for pretty much all of you. You may have seen it in a chemistry formula or something where I think there's a concentration formula where they get you to type it into your calculator, but you really have no idea what you're doing. You didn't even know what a log was. You just knew what the button was in your calculator and how to work through it. So I'm trying to get at this point now for you to get some sense of what are logarithms, how do I calculate them, what do they mean when I calculate them, and all that kind of stuff. And it's slow in the beginning because it is new. So having said that, it makes the importance of doing practice questions more so than ever. So it's going to be important that you go into your textbook and do these questions. Look at the answers in the back. Go back to the video if you're stuck. Send me a question if there's something you don't get. We'll try and get you headed in the right direction because we're going to try, time permitting, to get through the properties and laws of logarithms. And we'll finish up with that. And I'll show you a little bit about how to do some other bases on your calculator besides base 10 if you can't type those in. So that's where we're headed next. Good luck and reach out if you have any questions.